Good morning, students. In the last class, we have seen generalized heat conduction equation in polar coordinate system. In polar coordinate system, what is the 3D conduction equation? This is cylindrical coordinate system. This is what we have seen. And in this system, the coordinates are r, theta, and z. R, theta, and z we have considered. And then if you take the volume, no, the volume will be like this, where the second dimension will be r into theta, r into d theta. For considering the arc length, this is how you consider the arc length. So all of them are in meters. Okay, this unit of this one is in meter, unit of this one is in meter, unit of this one is also should be in meter. So that the volume unit will be meter cube. So I'll write it here. Okay, if I thought if I clarify this here, student will have a better clarity. So I'm writing it here again. Yesterday I did not write it, but now you carefully look into this. Okay. See, always when we consider units, no, our things will get clarified with like anything. Here, R is in meters. Anyways, you will measure it in meters. If you put d theta here without a dr, what happens is it is an angular dimension. Okay, angular dimension is a secondary dimension which you cannot consider here. So, if you have it as d theta here, it is not a length here, it is angle. Angle is measured in radians. So you cannot have a radian as a unit here, which is actually a secondary unit. So if you consider a unit here, what is happening? You having it in meters. So if you have it in meters, what happens? The whole thing will be in meter cube, so that the volume will be measured in appropriate SI units. That's the point here. Okay. So yesterday I have missed this particular point. I thought of saying it today so that student will have a clarity with respect to this. Okay. Some students they prepare little less while they go for the exam. They prepare well with the previous one, that is the Cartesian coordinate system, and they take that for granted and they write d theta here. Okay, but they miss this point. When they miss this point, no, they'll actually commit a mistake. So my request for all of you is look into the units wherever possible. When you look at the units wherever possible, the things will get clarified like anything. Right. So the regular story we have taken here, we have taken the dr, dz, and r d theta as three dimensions first. And then in three directions, what is the q? We have represented in the diagram. It is qr plus dr, q theta plus d theta, and then qz and qz plus dz we have defined. And then we have taken the difference of those two. Taylor series expansion we have considered for the infinitesimally small change that is happening in the system. And then we got the expression for qr minus qr plus dr. And then in the same thing in theta direction, we got it. And then for the same thing, we got in z direction also all the things we have taken. And finally, we have arrived at this equation for our polar coordinate system, that is our cylindrical coordinate system equation. So what varied is only this part varied. Okay, only the conduction part varied. The remaining two parts did not vary. Why? Because this conduction part is hugely dependent on the geometry, whereas the other two are not depending on the geometry a lot. Okay, so even though this QGen depends on the geometry, we have neutralized the effect of this QGen using the volume. We multiply it with the volume here. That's why the effect of it is neutralized in this particular term. Whereas in this part, the first term, you cannot neutralize that. You have to consider it because conduction is depending hugely on the geometry of a given case. So that is important thing here to be noted. And then this is the Poisson's equation. Okay, del square plus some constant will give you a Poisson's equation. This is a kind of same thing. Del square t in your polar coordinate system is this expression. And then This is your constant Q by K. So this will be a Poisson's equation. If you have simply Laplacian, that is del square T, if you have simply, then what you have is Laplacian, which is equal to 0. So this will be considered when you have steady and Q 0. You will have, this will be taken when you have steady temperature in 3D system. Okay, and in 1D system, if you take now, or if it is varying only with respect to R, only R part you will take. If it is only with respect to theta, you will take only theta part. Only Z, you will take Z. It is like that. Okay, and there are few more assumptions that you should look at. The assumptions are, the first thing is Kr is equal to K theta is equal to Kz, meaning the given uh, material which you have considered for conduction heat transfer is isotropic and homogeneous, and K is not varying with respect to the space. That's what you mean by almost these two statements are same. Okay, these two statements are almost same. So Kr is equal to K theta is equal to Kz means K is not varying with respect to space. That's what the meaning of it. And K is not varying with respect to the temperature. That is, K is not a property that is depending on the temperature. That is assumption you are taking here. But in reality, K may vary with temperature. In most of the cases, K will vary with the temperature. That's what we have seen in the introduction class to the conduction in the beginning lectures that we have considered. But here, as far as this equation is concerned, if you want to apply this equation, this assumption should be more or less satisfied in the case that you are considering or in the temperature range that you are considering. And then K is not varying with respect to space means the material should be isotropic and the homogeneous. That is, the material property should be same in the x, y, z direction, or here in this case, r, theta, z direction. That's what you will consider for your momentum equation also, momentum equation in your certain materials. When you consider it is an isotropic and homogeneous, you will consider. Like the same kind of homogeneous and isotropic we are speaking about here also, right? So that's all about your 3D conduction equation in polar coordinate system, that is your cylindrical coordinate system. Now, today we will move to the 3D conduction equation, 3D conduction equation in 3D conduction equation in spherical coordinate system. Spherical coordinate system. Yeah, better I put today's date here, 03/09/2020. Right. So this is also called as, let me write this in here. And here is this. Yeah, let me do something here. What's happening? She give me a minute. Let me close this completely and present it to you again. I'm sorry for that. There seems to be an issue with the software. Yeah, yeah, right, right. Yeah, it's came. or this is also called as generalized heat conduction equation. Okay, this is also generalized heat conduction equation. So here in this system, if you consider what will be your coordinates in any system, you better take what is coordinates first and then what is volume in the second place. If you take these two, everything will be clear to you. So here, since this is a spherical coordinate system, you will have radius, obviously. Any sphere you can consider, it can be like ball or anything like that, which is in spherical shape. R you take, and then there will be a theta, and then there will be one more angle, that is phi we will take. There will be two angles in your spherical coordinate system. One is r, other one is theta, other one is phi. So corresponding to this, if I have to take the volume, so corresponding to r I will have dr. Okay, so okay, dr into, if I take with respect to theta, it is r into d theta. R into d theta is for the theta. Okay. With respect to phi, what will be the, you know, the term to account for the volume here, or the linear dimension in the direction of phi? Can somebody tell me? Can somebody tell me what is the linear direction, sorry, linear dimension in the direction of phi? Can somebody tell me this one? Are you all there? Yes, somebody please tell me what will be the linear dimension in direction of phi. See, it is r into sine theta into d phi. It is not r into d phi, it is r into sine theta into d phi. See, this third dimension, that is a phi, that is the second angle that you are considering, is dependent on the first angle. So this third dimension is depending on the second dimension, and that you have to represent in this. Okay, so that's what you are going to do here. That's why I have taken sine theta also into this. So again, here you will have meter. This one is meter. This one is in meter, and then this one is in meter. Put together will give you a meter cube. Okay, so if you represent all of them in a diagram here, this is how it looks like. Okay, the infinitesimally small volume is considered in your spherical geometry, where you have dr and then theta, and this angle will be phi. This angle is theta, and perpendicular to theta you have phi. Okay, the plane perpendicular to theta will have phi. So in this phi, this dimension you want. Okay, this dimension is r sine theta into d phi. This arc length, this is how it is measured. This is dr r d phi r d theta. You already know this. Okay, so if I have to consider here uh, QR, what will be QR? QR is the, according to Fourier's law of heat conduction, minus K into A into dt by dr. You know this. What is A here? A is, you take out R and the remaining two. Okay, area perpendicular to the direction of heat transfer. So this area will be perpendicular to this. So what I get here is R into d theta, I'll get here, and then R sine theta into d phi, I'll get here. That will be your area into dt by dr is your qr. Next, what I want in deriving my generalized heat conduction equation is qr plus dr is required. Okay, where is this qr plus dr? Qr is going in this direction, okay, along with r. Along with R, QR is going, and QR plus dr is coming out. So QR plus dr will be equal to QR plus dou by dou r of QR into dr. How did I get this? This I got according to Taylor series expansion. Okay, by neglecting higher order terms, I got this actually. Okay, so this QR plus dr is equal to QR plus dou by dou r of QR into dr I'll have. Now, what I'll take is net effect of these two. This you can call it as dqr or qr net will be equal to qr minus qr plus dr you will have. This will be equal to mm, qr minus qr minus. I'm substituting this value into this here. QR plus dou by dou r of QR into dr. This is actually the same story that you have seen in the last class for your cylindrical coordinate also. So what I get here is minus dou by dou r of QR into dr. So here what I get is QR minus QR plus dr. You can take it. Now, what is my QR? I will substitute into this equation. Dou by dou r of QR is minus K. A is here r into d theta into r sine theta into d phi. This is what you will have. And then dou t by dou r you will have. So this I can close here. Yeah. So this minus into minus will be plus K I can take out. Here R is there here. This R I cannot take out because R is the variable here. So R will be inside. I'll take out the remaining part because what I want is K into dV here. So what I want to make this is K into dV into something. So what I want to do is I want to take out I want to take out this d theta and then sine theta and d phi outside because they are not variables here. So d theta into sine theta d phi I can take out. K is taken out. Yeah, everything is taken out. And then what I have is dou by dou r of r square is there here. This r into r will give you r square into dou t by dou r. So this is what you have here. And then here I want to make this. See here I have missed this dr. This dr should be here. So in first place dr should come actually to consider the volume. Okay. So yeah, now the equation is perfect. Now so k into dr into here I want to multiply nr so that I can get the volume and then r into sine theta into d phi. See, I have taken an r square here. Two r's are there here. To cancel out them, I have multiplied it by 1 by r square. Okay, dou by dou r into r square into dou t by dou r. Krishna Chaitanya, you want to say something? You can speak up if you want to say something. Yeah, k into what I can write this part as volume dv you can write into 1 by r square into dou by dou r of r square into dou t by dou r. This is what will be left out for your qr minus qr plus dr. So you're done with your r direction. Now, at this level, you have any doubt? I am moving on to theta direction next. Do you have any doubts at this level? Somebody? have any doubt, please ask me. Don't have any such doubts in relation to this. If you have any doubts, please, please. Uh,
డో బై డో ఆర్ ఇంటూ ఆర్ స్క్వేర్ ఇంటూ టీ బై డో అని ఇంకా సాల్వ్ చేయొచ్చు కదా సార్.
what? Yeah, you can solve it. Again, you have to take u into v. This is u, this is v. But most of the times it will be left out here. Okay. If you want to feel like solving, you can solve it. Okay.
ఓకే సార్.
It varies with the situation. Okay. In a given case, you will take it up like. In some cases, the temperature will vary only with respect to theta and z. Theta and
ఓకే
phi. Then in that cases there is no meaning in doing it. Likewise, just to for making it simple, it is left out like this, and most of the textbooks follow it this way. If you feel like doing that, you can go do it. It is simply differentiation of u into v. You can definitely do that. No issue.
ఓకే సార్.
Right. I'll move
So,
on. Yeah, tell me.
in the above equation, R is differentiated with respect to dt and d phi, no sir. How can we take R separately and those terms separately?
What I am doing here is a partial differentiation. I am not doing a regular differentiation or the what do you call definite differentiation, I can say. Okay, this is a partial differentiation. So when I say partial differentiation, you consider only one variable is varying, the other variables you will not consider. Okay, that's what is the partial differentiation, isn't it? That's what you have learned in your mathematics
Yes, sir.
course. Yeah. So what I'm doing is I'm considering each direction here. Okay, that's what we have been doing in even in the previous derivations also. So the same thing we have done here also. Okay. I hope I have answered your question.
Yes, sir.
Is it? Yeah. Thank you. Thank you. Right. Moving on to theta. Okay. Let's write it for theta now. Theta. Q theta. What it is, I will write here minus k into a into dt by. Let me wait here. Let me write the volume again here so that I can explain it better. Dr into r d theta into r sine theta into d phi. This is what your dimensions are. These are the 3 dimensions. And then here I'm considering with respect to theta. So what I should write here? This whole thing I should write here. So I'm writing the whole thing. I've written that. And then come to your a minus k. Probably to save space, I'll write it here. Minus k. A means without this, these two you have to write. Dr into r sine theta into d phi. This is area perpendicular to the direction of heat transfer. Right. So this will be dt by r into d theta. That will be your q theta. Then what you need is q theta plus d theta. I hope I'm showing it here. No, I am not shown theta to you here. The theta will be something like this. Okay, since this is theta direction, this will be your q theta, and this will be your q theta plus d theta. Okay, so that's what we are writing actually here. Yeah. So if you have to take this according to Taylor series expansion, it is q theta plus dou by dou theta. When I take dou theta here, it is again r d theta. Okay, this thing I have to take of q theta into again r into d theta. Okay, this is how it will be like. And then this, what I need is dq theta, which is also equal to d theta net. This is q theta minus q theta plus d theta is equal to q theta minus, I'm substituting it here. What I get is q theta of dou by r into dou theta into q theta r into d theta. This is what I get. So These two will get cancelled. When these two are getting cancelled, what I have here is q theta minus q theta plus d theta is equal to minus dou by r into dou theta into q theta. I will substitute here. This is my q theta. It is minus k into dr into r sine theta into d phi, and this value I have to take it here. dt by, see, I'll not put dt here, I'll put dou here because I'm considering the partial differential equation. Dou t by r into dou theta. Right, minus into minus will be plus, and then here what I want is k into dv. I'm taking k outside. For dv, I'll take out dr outside, and then r also I can take it outside. So this will be r sine theta. Instead of writing this r sine theta first, I'll
T
write this r into d theta here. This I will write first here. Since this is outside, okay, you can directly take it here, r d theta, and then here r sine theta into d phi is there. This theta you cannot, this sine theta you cannot take out. Yeah, sorry. Sine theta you cannot take out. Only you can take r into d phi you can take out. Sine theta will be inside. Sine theta has to stay inside itself. And you have this 1 by r here. That 1 by r, I am writing it here. And then, yeah, here. This 1 by r is also there here inside. That also I can take out and write it like r square. And then dou by dou theta of k I have taken out, dr I have taken out, r sine theta only is the thing remaining. Sine theta will be within my bracket dou t by dou theta. So this is your equation now. Here, what I want is, I want the whole volume here. Sine theta is missing, so I'll multiply and divide with sine theta. So dr into r d theta into r sine theta into d phi, 1 by r square sine theta dou by dou theta of sine theta into dou t by dou theta. Okay, so this is your equation now. You can simply write it in terms of dv, k into dv into 1 by r square sine theta into dou by dou theta of sine theta into dou t by dou theta. So this is your q theta minus q theta plus d theta. You need little more patience compared to your previous spherical, sorry, cylindrical coordinate and Cartesian coordinate system. If it can take that little patience, you can solve this. Right. Let's move on to 5. What is 5 direction? If it is 5 direction, again, let me write the volume here. It is dv is equal to dr into r into d theta into r into sine theta into d phi. Okay. D phi. This is your volume now. And then here, what we will do is we will take q theta is equal to minus ka into dt by what is should be in the denominator. Since it's not theta here, it should be phi actually. My errors, I have to help me out. Yeah, so it didn't make any issue for me now. So what I have to take is q phi actually. So what I have in the denominator will be this value. Okay, this is very important. This one I have to have here. And then when it comes to a, I can have the remaining 2 here. That is dr into r d theta into dt by r sin theta into d phi. Okay. Mm, yeah, we are done with q phi. Now q phi plus d phi is equal to q phi plus dou by what is this r sine theta into d phi. This dou phi into q phi into r sine theta into d phi. This is what you have according to your Taylor series expansion. Higher order terms neglected. The same story. So what I have here is q d d q phi. This is also q phi net is equal to q phi minus q phi plus d phi. We will have this is equal to q phi minus this. I'm substituting here. So what you get here is q phi plus dou by r sine theta into dou phi into q phi into r sine theta into d phi. I will write it again more clearly in the bottom. So this is q phi minus q phi plus d phi is equal to these two getting cancelled. What I have is minus of dou by r sine theta into dou phi into q phi into r sine theta into d phi. It is not dou, it is d. Right. So you have this. Now in this q phi, I have to substitute this value minus k into this whole thing. So this is minus of dou by r sine theta into dou phi of minus k a. A is dr into r d theta into what I have as dou t. Since I'm considering partial, I'll go for dou t by r sine theta into dou phi into r sine theta into d phi. This is what I have here. And then what I need is k into dv here. K I'm taking out minus into minus plus. And then dr I will have out here because it is d phi which is varying. I don't have any d phi here. So I can take out this part very comfortably outside. R into d theta has come out. And this one I'm writing it here. R sine theta into d phi. Pawan Karthik is writing something. I don't know what he's trying to communicate. But this I have taken it on this side so that this will be your volume completely. And here I have r here, I have r here. I can write it 1 by r square. I have sine theta here, I have sine theta here. I can write it like sine square theta. Okay, into dou by dou phi of dou t by dou phi I will have. That's it. So what I have here is k into dv into 1 by r square sine square theta into dou square t by dou phi square. So this is your q phi minus q phi plus d phi. This is your equation. And now what I should do is I have to take q conduction plus q gen is equal to q stored. This is my balance energy balance equation. So if I take conduction, it is I will write it like dq r plus dq theta plus dq phi plus q gen. This should be small q. I'm sorry for this. It should be small q is equal to q stored. This q stored is nothing but mcp delta t. So if I take this here and this, what I have here is k into dv into, if I take with respect to r, what I got is 1 by r square into dou by dou r of r square into dou t by dou r plus, see, I'll be closing a little fast, kindly bear with me. 1 by, with respect to theta, what I have is 1 by r square sine theta into dou by dou theta of sine theta into dou t by dou theta plus uh, the phi direction. What is the value of it? It is 1 by r square sine square theta into dou square t by dou phi square. This is your first expression plus q gen. This plus I'm writing actually here, I'm continuing it here, is equal to
Sir,
mcp. Yeah.
at last 1 by r square sin square phi, I think.
Huh?
The
What?
last one. D d theta dq phi.
D? You are referring to which equation?
Last
Which,
term, sir.
Rahul? This one,
Yes,
huh?
sir. Last term. 1 by r square sin square phi, I think.
Sine square
Phi.
theta. It's not phi. R square sine square theta. What we got here is theta. It's not phi.
Oh, okay, sir.
Phi. It is dt by d small t, where small t is representing your time. Right. So what I have here is k into dv into del square t. Del square t is this whole equation in your spherical coordinate system. I'm simplifying it into q gen is equal to mcp dt by d small t. So when I divide it with this k into dv, the whole thing, then del square t plus q gen by k is equal to m by dv will give you density, and cp by k into dp by. So what you have here is del square t plus q gen by k is equal to rho cp by k. You get here. This value is, it is referring to your rho. It is rho cp by k, which is nothing but 1 by alpha into dt by dt. Okay, all right. So this is your equation simply. This is simply like your previous equation only. Only thing is your del square t has changed. So that's all for today.